Welcome to another segment of High School Geometry with Netz and Weichel. This is Mrs. Netz.
And this is Mrs. Weichel.
And today we are starting Chapter 6, Similarity, 6.1 Dilation. What will we be learning? Well, we will be learning how to use scale factor to make a larger or smaller copy of a figure that is also similar to the original figure. Why is this important? Well, understanding that dilations may mean a reduction or an enlargement in size of a figure is important since dilations produce similar figures. It is also critical to be clear that the shape will remain the same. How will we know we mastered it? Well, you'll know you have it mastered when you can accurately use dilation to stretch or shrink geometric shapes proportionately.
Awesome. Let's go ahead and get started. First thing is, what is a dilation? A dilation is a transformation that changes the size of a figure. So for the first time, you're going to be moving shapes around a coordinate plane where your shape is not going to stay the same size.
Think of dilation for those of you who wear glasses or contact lenses. I'd be willing to bet you've probably had your pupils dilated.
Probably.
So you can think of dilation as something that when your pupils are being dilated, they open up very large and they let all the light in. That's pretty much what we're doing.
So I have some examples here of dilation. So here's a paper airplane that is dilated with the blue and the pink, a rocket ship, the planet Saturn, and a pushpin. So those are all kind of what you're going to be doing today in this lesson. Similar to a rotation, in order to be a dilation, you need a center in which you are dilating from. When you were in grade school, you probably did scale drawings of things. A scale drawing is similar to what we're doing, but a scale drawing isn't from a central point, whereas a dilation is moving in towards or away from a point. So you can see in my example here that my blue triangle is closer to that center point than the maroon triangle.
Sure. And you can actually think of it like this. When you were working, many of us have worked on PowerPoint or in Word where we've copied in a picture, and then what we do is we need to make that picture bigger. And my mom, for some reason, always pulls the picture downward, which is nice because it makes everybody look very skinny.
Yes.
It's really nice. But then there's some people who pull the picture from the side and then everybody looks very short and wide.
And fat.
Yeah, like my head is twice as wide. It's kind of bizarre. So those are not necessarily a dilation from a particular point. However, if you were to take your picture and pull from one of the corners,
and hold the shift button.
And hold the shift button, what you were doing, or hold your mouse, then what happens is you are dragging proportionately the length and the width. So therefore the picture is growing by the same proportion on both the height and the width.
I believe in the example you're talking about that if you're pulling in the bottom right corner, the top left corner does not move.
You are exactly correct.
So everything is moving away or towards, depending on if you're getting bigger or smaller, from that point opposite what you're dragging.
Yeah, for example, like in the picture we have on the screen right now, if I were to if I wanted to make the maroon triangle, what I would do is I would pull on that bottom right corner of the blue triangle and it would stretch it down to become the maroon triangle. Basically, it's stretching away from what we could imagine being the top corner of a picture where that point of dilation is, or the center of dilation. My bad.
So there you go. So to be a true dilation, you're going to have a center of dilation, which is your fixed point. That's the one not moving. So like when you did rotation, there was a fixed point. Everything turned around it. With a dilation, there's a fixed point that everything is moving in towards or away from. In order to do a dilation, you need to know that center point. You also need to know how big you're making your dilation. Is it getting bigger? Is it getting smaller? That is called your scale factor. It's the size of dilation. When your scale factor is greater than 1, so any number greater than 1, it means that your shape is going to be getting bigger. You're moving away from that center point.
And the reason for this is you need to remember your scale factor is what you are multiplying by. So if I multiply something by 2, it becomes 2 times as big. But what happens if you multiply something by a half?
So that's when you have a scale factor greater than 0 but less than 1. If you're taking half of everything, your shape is going to get half as big or smaller, which is the example on the right side.
Wait a minute, what about a negative?
Negatives are going to bring in your composite figures. When you have a negative x value or a negative y value, that means you're rotating or reflecting depending on where your x and y are. So as far as a straight dilation, you're never going to have a negative, ever. If there's a negative there, it means you're doing something else other than just dilating.
So it means if you have a negative and either a fraction or a whole number, that means what you are doing is a composite transformation.
So students all the time, when you see like a negative 2x, that 2 is the actual dilation. The negative, that doesn't mean we're getting smaller. Students sometimes forget, you guys are usually good with the greater than 1 is bigger and the less than 1 is smaller. They forget the greater than 0 part. So make sure you understand that negatives mean something else. You're looking at just the numeric part, just positive numbers for our dilations.
So think of it like this. Smaller is going to be your fractions or decimals less than 1. And when you're getting bigger, you're going to have greater than 1. But
Yep.
Never negative.
Never negative. All right. What's preserved? I have an example here of a dilation. You can see that the shape is still preserved. We have 2 right triangles here. The fact that they are 2 right triangles, we know that our angle measures are preserved. So the right angles are easy to see, but know that angle H and H prime are the same still, and S and S prime are still the same. So the other thing is orientation. Remember, orientation is when you start on a letter and you go around clockwise or counter. For both of them, you do the same thing. You can see we're saying the same thing both times.
Now, think about this when it comes to angle measure, because I know a lot of students really struggle with the idea of, I'm going to make this object 2 times as big, so therefore the angles need to become 2 times as big. Think about a square. I can have a square that's 1 inch by 1 inch, and I know all the angles are 90 degrees. But could I have a square that's 100 feet by 100 feet?
You could.
So now are the angles 100 times bigger, like 9,000 degrees by 9,000 degrees?
No, silly.
90 by 90 by 90 by 90. You have 90 degrees on all 4 angles. An equilateral triangle, we know that all 3 angles are the same. 180 divided by 3. 60 degrees each.
60 degrees each.
So I can have a really tiny equilateral triangle, or I can have like a gargantuan. I don't know how big that would be, but it would be big.
Really big.
Really big. So does it matter? What would the degrees of the angles be?
It would still be 60 degrees.
Because you have 3 sides, and if you remember our formula to figure out the degrees for the angles of a polygon is n minus 2 times 180. That n minus 2 times 180 does not care how big the sides are.
Exactly. All right. What is not preserved? Now, for the first time in this class, our side lengths are not preserved because, again, they're getting bigger or smaller. So what's changing is the perimeter of the shape, the size of the shape's side lengths. And then, of course, position. You're moving in towards a point or away from a point. So you're going to be in a new location. Okay, so because of what is happening, a dilation is not a rigid transformation because size is not preserved. So you can see up here I have our 4 transformations that we've talked about. In this first one, I hope you can see that this shape here is reflected over this vertical line. And reflections are considered to be a rigid motion, as we learned in our rigid transformation unit. Over here, we have our triangle down here is translating left and to the right to make this triangle, which is a rigid motion. And then lastly, we have this triangle rotating from quadrant 2 down to quadrant 3. That is a rigid motion. So these 3, what they have in common is that all the shapes are congruent. from start to finish.
The other thing that you can think about is a rigid transformation is anything that you can do with a piece of furniture in your house. You can reflect it. You could flip a chair upside down. It'd look awkward, but you could do it. Translation, well, I think almost all of us have gotten down on the floor and pushed a piece of furniture with our feet, or at least I have.
I'm sure most have.
Yeah. And rotation, could you spin your bed around the room and have it sit somewhere else?
Definitely.
Of course.
What you can't do is dilate.
You can't stretch your bed twice as big.
Be awfully cool, but no, you cannot.
Dang it, you can't like stretch it to be or shrink it to be half as big?
You cannot.
Bummer.
My feet always hang out the bottom of the bed. I would love if I could make a longer bed.
Ooh, if you could just dilate it, if you could just pull from one corner and make it bigger. Yeah. My feet don't ever reach the end of the bed.
It's a tall person problem. All right, so dilations are not a rigid motion because, again, your size is changing. So it's important to keep this as a separate entity.
Rigid is like furniture, period.
All right, how do you know when to do it? Verbal, it'll say dilate by a scale factor of 2 from the origin, or whatever scale factor you want to use from whatever center you want to use. Those can be anything. Typically for beginners, you stay in the realm of like 2 or a half, because those are the easiest to work with. A lot of times on the coordinate plane, it will be from the origin. And similar to with our rigid motions, if you're centered around the origin, you are able to write a mapping rule very easily.
So could I then say by a scale factor of 1/2 from the point -1, 5?
You could.
Oh, I said -1. We said no negatives.
The scale factor was positive, though.
Oh,
remember, on the
1/2.
coordinate plane, you can have positives and negatives.
Got it. Sorry, confused.
So if you look at what I have here on the screen, you can hopefully see your scale factor is the number that you are going to multiply. It is important that you make a note that you are multiplying to both x and y the same exact scale factor. To be a dilation versus just a horizontal stretch or shrink and a vertical stretch or shrink, both x and y must be stretching and shrinking exactly the same. If it's different, then you're just stretching or shrinking. You're not dilating. And then notation, you have a capital D with a subscript. The subscript is showing you your center and scale factor. So hopefully by now this is our, fourth lesson kind of in this world of transformations. By now this should make sense. If not, always reach out to me.
But notice that the biggest difference with dilations is now we are multiplying our variables by a coefficient. For those that need a reminder, coefficient, that is a number that is being multiplied by the exponent, or sorry, not the exponent, the variable. So 2 is a coefficient to x.
So, yeah, this is the first time. So up until today, you were only adding or subtracting numbers for your translation rules. Now we're actually going to bring in multiplying. Well, again, the nice thing, it's always the same number for x and y.
Yes, it is. It is.
All right, so hopefully you have your compass and straight edge. If not, pause the video and go get it. We are going to dilate this segment by a scale factor of 2 from center C.
Looks hard, but it's way easy.
Very easy.
Go grab your tools. Hurry.
Okay, so I did not even write out the steps because it is so easy. So the first thing you guys are going to do is you are going to, with your straight edge, you're going to draw a line from C through A.
Easy.
After you're done doing that, you are going to measure the distance of C to A.
Another easy step.
Super easy.
It's almost like copying a segment. Step 1 to copying a segment.
Very much like that.
It's actually exactly like that.
All right, so there's my distance. Now, here is tricky part, yet super easy part. You are going to dilate by a scale factor of 2, which means the distance A is from C must be doubled. Where students like to mess up here is they go 2 beyond A. You need to count this distance as 1. And I did not go big enough. There's 1. And I actually advise you to mark the arc through A, just like that. That's going to count as 1 to help you remember that. I need 2. So we're going to go just 1 more.
So think about it like this. If I said I was 2 times as tall as somebody else, you would say that it takes 2 of me to make them. Well, just like here, what we are saying is it takes 2 of these segments to make the original segment. So to make segment AC double big, you would need to now have A prime C.
Yep. All right, so now you're going to do exactly the same for C to Z. You're going to, with your straight edge, draw a line. You're going to measure the distance C to Z. And then again, I would mark through it. That's 1.
Now we're copying a segment. Watch.
We're
You
copying a segment.
And boom.
And 2. Once you've done that, you have now doubled the distance A and Z are from C. So now with your straight edge, you're simply going to go through and you get your line segment. I'm a little off. I'm going to cheat for video purposes. There we go. So a couple things we know. We know that the distance A prime is from C is double the distance A was from C. Same with Z prime. We also know that the length of A prime Z prime is twice as long as AZ. We know that that's all you need to know right now.
Yeah, I think that's it.
Okay. We're going to do the same thing again.
With an angle?
With an angle.
Shut up.
So again, we know the length of A prime Z prime is doubled. We're going to go through the same exact process, but now you have 3 points that we are going to dilate.
But wait a minute. Didn't we say that angle measure is preserved, so it won't change? So why are we...
We're going to test that theory out right now.
Okay, because wouldn't it just be the same?
It should be, if you do your construction correctly.
All right, let's try it.
All right,
so
you're
I'm guessing draw a line.
Draw a line.
From O to R.
And then you are going to measure
O to R.
O to R, and you're going to double that distance. So you're going to make your 2 arcs. So right here is, whoops.
Oh, is your compass big enough?
1. And there is 2.
I think your compass is a little short. Like you're not on point R.
Mrs. Weichel forgot her glasses today, so...
That and Mrs. Netz feels like she's still grading construction projects from chapter 4. So all the way, so you make your mark, and then you have to, so we're going to make our mark, and then you have to make sure you move your compass right to the mark that you had previous. And then mark again.
All right, so I'm not going to try. I think that they should be able to move J and W the same way. So pause and do.
Go, go, go.
Okay, so this is the angle you guys should have gotten. And as Mrs. Netz pointed out, we talked about how angles are preserved when we dilate. Well, you can see the angle that I started with is 70 degrees. Even though the side lengths have doubled, because our scale factor is 2, the angle is a lot bigger in size that it's taking up. If you remember when we talked about our constructions with angles, you're actually copying the degree when you copy an angle. So same here, when you dilate, you can see we still have a 70-degree angle, even though the space it's taking up is larger. Remember, the arrows mean infinite. So I can make that just as long without changing the actual dilation. The angle did not change. So
you could pick up RJW prime and put it on top of RJW and it'd be the same.
You should be able to, yes.
That's pretty cool.
Yeah. So this is a huge, huge thing that you guys, I would write this at the top of page, what are we on, 18?
Mm-hmm.
Side lengths are affected by scale factors. Side lengths will become however much bigger or smaller the scale factor is saying. Angles,
same.
Same. They do not change no matter what. If you are dilating, your angles are exactly the same.
So you should be writing right now that angle RJW is congruent to R prime, J prime, W prime.
They are exactly the same.
Yeah, all day long.
All day long.
Let's do another one.
All right, so now you can go ahead and put your compass and straight edge. Well, not your straight edge. Keep your straight edge. You can put your compass aside, though. Now we're going to do something similar to what we were just doing, but we're going to use the coordinate plane instead.
We're going to move a fox around.
So because we are going, or actually you need to pause the video and go ahead and graph triangle FOX. All right, so the first thing that we are going to be doing, you're going to be dilating FOX by a scale factor of 1/2 from the origin. So I'm going to go ahead and highlight that. I'm going to highlight it in pink, and I'm going to draw my triangle in pink.
So think about this. You need to look at how far away F is from the origin. So it is up 10 over 2. You need to go half of both of those. So half of up 10 is up 5. Half of over 1 is, over 2 is over 1.
So F prime is going to end up right here at 1/5.
We're going to do the same thing with O and the same thing with X. So if you'll notice, O is up 8 over 9. We've got to do half of that. So it'd be up 4 over 4.5. So you'll go halfway through one of the squares.
And then lastly, X is right 8 up 2. So we're going to go half of that distance, and we're going to go right 4 up 1. And you can see I have my prime notated triangle, F prime, O prime, X prime.
That was actually kind of easy.
Yeah. When your center is the origin, again, you can really write a rule. All we were doing was taking all of our X's and Y's and dividing by 2. I like how Mrs. Netz was explaining it, though, because if we were to ever change the center of dilation, you would do exactly as she described. You would measure how far each point is from whatever center you're using. Again, in this case, it was the origin, but we could do it from any point. You could have dilated FOX from point X. Then X isn't moving, and F and O would be coming in half the distance towards X.
That's
so it
easy.
could be anywhere. All right, so from here on out, it is 100% review from our rigid motion unit, which was chapter 2, I believe.
Well, since it's review, can't they do the rest?
I would love it if you guys paused the video and went ahead and did this. So
what
first,
if we tell them first what colors?
that's what I'm going to do.
Oh my
You read my mind.
genius!
So you're going to translate left 4 up 1. I'm going to do that in green. Then you're going to rotate 90 degrees counterclockwise around the origin, and I'm going to do that in blue.
Remember, counterclockwise goes to the left.
And then last, you're going to reflect over x equals 0. And remember, x equals 0 is actually the y-axis.
You got this.
Okay, so you guys should have paused the video. Hopefully, if you didn't, do it now. Because you should be able to do the rest of this by yourself without our help.
If not, spoiler alert.
Yeah, right. All right, so we're going to go left 4 up 1. So 1, 2, 3, 4 up 1, and you're going to end up with double prime F right there. 1, 2, 3, 4 up 1. 1, 2, 3, 4 up 1. Then you're going to rotate the triangle 90 degrees counterclockwise. So I'm just going to look right here at X. I see that I'm up 2. If I'm going 90 degrees to the left, we're going to end up right here. Same with O prime. We're going to go 90 degrees to here. And then F double prime ends up down here, and F triple prime.
Now we're going to flip this thing, huh?
Now we're going to flip over the y-axis. So again, I'm going to start with X, you're left 2, so I'm going to go right 2. Left up, right up, left down, right down. Same distance from that y-axis. And there you go.
Very cool.
That is dilations. Hopefully you feel like you can identify the properties of a dilation. As we discussed, what you're doing to X and Y must be the same. How you're stretching horizontally and vertically must stay the same. And you should be able to perform a dilation with a compass straight edge and with an X and Y coordinate plane. And that is it. Hopefully if you need help, you come see us or talk to us or email us or remind us, whatever.
Hey, Mrs. Weichel.
Hey, what, Miss Metz?
What did the mum triangle say to the baby triangle?
I don't know what.
Stop being Illuminati.
Is that because their symbol is a triangle? Isn't it? The Illuminati?
You know what? It's what I had for a joke. Sorry.
That's pretty funny. All right. Thanks for joining us in 6.1. We will see you in 6.2.
6.2.